Welcome everybody, Isaac here. Today I'll be showing you how to create and do something with a very simple PennyLane circuit. Before getting started, make sure you watch our video on how to install PennyLane, linked in the description below. In this video, our goal will be to implement this circuit in PennyLane. It's a simple 2-qubit circuit that applies a few quantum operations and gates, and then measures the poly-z expectation value on 1 qubit. Now, if you're unfamiliar with any of these concepts that I mentioned, like the expectation value or the poly-z operator, no worries at all. We won't be explaining them in this video, but our quantum codebook is a great place to get up to speed, and it's linked also in the description down below. Let's go to a Jupyter Notebook and get started. Okay, here we are in our Jupyter Notebook, and as with anything, we start by importing PennyLane and some other utilities like NumPy. So we're going to import PennyLane with the alias QML, and we're also going to import PennyLane's wrapped version of NumPy as NP. So to code a quantum circuit in PennyLane, we need to marry two different ingredients, a device and a quantum function. Let's start with the device. So in PennyLane, a device refers to an object that can apply quantum operations and return classical quantities like measurements. This could be a real piece of quantum hardware or a simulator. And today we're just going to use a simulator device called default qubit. So to define a device in PennyLane, all we do is call qml.device and give it two arguments, a string associated with the device itself, which is a simulator we're going to be using called default qubit, and a keyword argument associated with the number of qubits in our circuit. Now in PennyLane, we also refer to qubits as wires, so we're going to say wires equals 2. The next thing to define is the quantum function, which provides the device instructions for what quantum operations to apply. Quantum functions are made similarly to a regular Python function that we'd all be used to, with a def statement and the function name and a list of arguments. Within the body of our quantum function is where we put the quantum operations themselves, one per line. Now by default in PennyLane, all qubits are initialized in the 0 state, so I don't need to do anything there. I just need to go to my quantum operations. So the first one is a poly-x operation on the second wire. Now remember, Python indexes from 0, so we say wires equals 1, which means the second wire or qubit. The last gate in our circuit is a Y rotation gate. We're going to call it by qml.ry. The first argument it needs to see is the angle of rotation itself. I'm going to call this theta. And then the next argument is just the wire that the operation gets applied to, which is wire 0 in our case. Now I'm going to leave this theta angle as a variable, so I need to also put it in as an argument into my quantum function called circuit. And lastly, we need to return the expectation value of the poly-z operator on the first wire. So we're going to type return qml.expval, which means expectation value, and then the operator we need to take the expectation value of, so qml.poly-z, and on wire number 0. All right, so we've listed instructions for our device to perform via our quantum function. But how do we actually get to executing those instructions on the device? In PennyLane, the units of quantum computation are represented using an object called a quantum node. The quantum node encapsulates our device and our quantum function. So how we do this code-wise is through a decorator above our quantum function, qml.qnode, and we just provide it the device object we defined in our second code block here, dev. Now, decorators themselves are also a bit of an advanced topic in Python, but we've provided a link in the description below as well for you to learn more about decorators if you'd like. All right, so we have everything we need to actually simulate our desired circuit. So let's just test it out for a particular rotation angle. Let's say pi. And you can see we get an actual value of 1. If you work this out analytically, this is actually what we should be getting. But we can actually execute this circuit and run it as many times as we want. So let's try like a range of rotation angles to execute our circuit with and plot the resulting expectation value. Now to do the plotting, I'm just going to import matplotlib. Then I just need a list of angles to try my circuit on. So I'm just going to call numpy.arange, go from -pi to pi in units of 0.01. I'll collect all my circuit outputs in an object called measurements, which I'm just going to initialize to an array of all zeros. Then I just need to loop through all of my angles that I defined and collect the measurements. And in plotting the results, you see a nice kind of sinusoidal pattern, which you would expect to see if you worked out everything analytically. And that'll do it. You now have the basic structure required to create and run your own circuits in PennyLane. If you have any questions, please post them in the comments down below or in the PennyLane forum, which we've linked in the description. If you found this video useful, give it a thumbs up and make sure to subscribe for more quantum computing content from Xanadu.